Welcome everybody to this first presentation of the Solver Day at CU at Work. So one question that all the companies presenting here today have in common is the question of how fast is their solver? And when they implement a new technique, does this improve the performance? So this is why we will first talk about how to benchmark software for mathematical optimization. And for doing so, we will touch on three topics in particular. This is performance variability, statistical tests, and best practices for benchmarking. Let's go.
As a motivating example, look at this statistic of the performance improvements between two versions of one MIP solver. This is already some years old and uses the now outdated MIP-lib 2010 instances. On the x-axis, we see the 87 instances of the benchmarking set. On the y-axis we see speed-up factors comparing the new against the old version of the software. If we consider the geometric mean over the solution times, the new version got around 30% faster on average. But what does that mean with respect to an individual model? Did each model also get about 30% faster? Intuitively, that might be something to assume, but as you can see, this is far from reality. Actually, for these particular releases, only half of the models got faster, about 10% did not change performance, and 40% ran slower with the newer version. The reason that the observed average performance is so good is that the individual speedups are larger than the individual slowdowns. For example, there are only 2 models that got slower by a factor of more than 2, but 12 models that improved by a factor of more than 2. But why are there so many slowdowns? There are 2 possible reasons. First of all, there might of course be features that lead to an intrinsic slowdown for some model. Consider for example a new expensive presolving operation or start heuristic that does not find anything for a model, but just uses time. The other reason is performance variability. Performance variability is a major issue that has to be taken into account when benchmarking optimization software. Let's discuss it in more detail. The term performance variability refers to a change in performance that is observed after some changes that we would expect to be performance neutral. One example is a change the input format, which means reading an instance as an MPS file instead of as an LP file, or vice versa. Indeed, although the input instance remains exactly the same, changing the format might lead to a different solution path for all MIP solvers currently on the market. In fact, for the 2 file formats, columns and rows will be input in a different order, which might cause a different tie breaking internally, hence a divergence in the solution paths. The solution path is the sequence of steps that a solver takes to reach the optimal objective. The first place where such a path change occurs is often in the solution of the root LP. Random tie breaking in the ratio test or the pivot selection might lead to a different simplex step. Due to primal and dual degeneracy, the solve ends up with a different optimal basis, in most cases even a different optimal solution vector, with the same optimal objective of course. Due to the very heuristic nature of MIP solvers and the potentially exponential blowup of branch and bound, such little changes might make a huge difference. Imagine as a most extreme case a binary problem without objective function. All feasible MIP solutions are vertices of the LP relaxation. Once the solver finds one of them, the solve will immediately terminate. However, only very few vertices might be integral, but all will be LP optimal. A slight change in the simplex might make the difference between solving the instance with the initial LP in a few seconds by pure chance or branch and bound running for hours. This example is less artificial than one would hope. Instances like this are somewhat frequent. Moreover, also solving the same instance on a different operating system might lead to a different solution path for many solvers due to different implementation of math libraries. Express, however, is unaffected by this kind of variability. Running Express on the same instance, no matter whether on Windows, Mac or Linux, will always produce the same solution path. This is a useful feature when different people working on the same project have different preferences on the operating system to use. Changing the number of threads might also affect the performance of a solver, even though in Express, This can be avoided by setting two controls, one for the LP and one for the MIP parallelization. Performance variability is mostly a burden to developers. One might believe to see a performance improvement, where in reality there is only performance variability. This might lead to wrong conclusions in solver development, but also in scientific writing, if experiments are not carried out carefully. Hence, when doing comparisons, performance variability should always be taken into account. A first simple countermeasure is to use big test sets, which makes it more likely that positive and negative outliers caused by variability cancel out. On the slide, you can see some statistics that describe a set of experiments, for which we ran express on the benchmark set of MIP-lib 2017. For each problem we generated 10 different variants by permutating the column and row order. One result of this experiment is that about half of the instances in the MIP-lib benchmark set have a variability of more than a factor of 2. Moreover, for 30 of them, this factor is even larger than 10. The larger the test set, the more these effects cancel out. On the 240 MIP-lib benchmark instances, the difference between the best and the worst permutation is about 4%. For the internal express performance test set of 1000 MIP instances, this difference is estimated to be less than 1%. At the same time, however, variability can also be utilized to artificially inflate information on the test set. As indicated on the previous slide, one may permute the instance. This is change the order of columns and rows in the matrix. Of course, this still remains the very same instance. But since the solver will see it the columns and rows of the instance in a different order, type-breaking decisions might be taken differently. Permuting instances is a way of causing performance variability on purpose. When running an experiment with several permutations of each model, we can better distinguish between structural improvements and random noise. By looking at the variation in the performance instance per instance, we will be able to tell if an improvement is consistent on that instance. If an algorithm solves all of its permutations consistently better than another algorithm, then the first one can be safely considered better than the second for that particular problem. On the other hand, if the difference in the performance is positive in half of the case and negative in the other, we are probably witnessing random noise. As you can imagine, permuted instances can be used to blow up a small test set to improve the chance that performance variability effects cancel out. Another use of performance variability, very important in commercial software development, consists in imitating performance on unknown instances from the same application. This might be necessary because, very often, customers only provide one single example, although developers always ask for as many examples as possible. Indeed, the more examples are provided, the better the recommendations that can be given. As we see, one way of enforcing performance variability is by using random permutations of the matrix. A disadvantage of this method, however, is that it might lead to a loss of structural information. A matrix that has the property to be visually structured in a nice way in its original form might lose this property after being permuted. Using different random seeds for the pseudorandom number generator is another way to inject performance variability into a solver. This does not have the structure loss problem, but leads, on average, to much less variability. There is a recently described method of using a special kind of permutations, namely cyclic shifts. Permutations of the instances are not generated completely randomly, but just by inducing one breakpoint on the rows and one on the columns, then shifting the whole matrix cyclically by this particular offset. This combines the advantages of the two previously mentioned methods and is therefore a good way of inducing performance variability. If you continuously work on a project, always benchmarking on the same problems, there is of course the risk of overtuning. Again, performance variability can help to reduce this effect. It is advisable that you change the set of permutations as well as the random seed at a frequent level. Another best practice for conducting computational studies is the use of statistical tests. The idea of a statistical test is to set up a hypothesis, for example, solver A is faster than solver B, and compare it with a so-called null hypothesis, which denies this relationship. By statistical methods, we compute how likely it is that the null hypothesis holds. More precisely, a statistical test expresses the likelihood to get a result that looks as extreme as the given result, or even more extreme, when observations are drawn at random. In other words, it gives the probability that the observation is just the effect of random noise. This probability is called the p-value. If this probability is low, our original hypothesis is probably true. When the p-value is less than 5%, the result is typically considered significant. The reason for this detour of using the null hypothesis is twofold. First of all, it gives a common framework. We always compute the chance that the difference between two observations is random. Second, more importantly, the behavior of random changes can be captured in a concrete formula, once we specified assumptions on the underlying distributions and data types. There are two different statistical tests that are frequently used for computational experiments in mathematical optimization. The McNamara test is used for categorical data. Categorical data is data from finite, typically not ordered sets. The most common case is a yes-no question. For example, is this solver more likely to find a feasible solution than the other solver? Yes or no? Is it more likely to solve the instance to optimality? Yes or no? The McNamara test considers 2-by-2 contingency tables. The important information are the two numbers on the counter-diagonal. That is, the numbers of instances for which the answers by the two algorithms differ. From this, the McNamara test computes a test statistic which can be shown that it would follow a chi-squared distribution for a random draw. From this chi-square statistic and the assumed distribution, one can look up the p-value. Then, there is the Wilcoxon-signed rank test. This is used for numerical data, for example run times. The Wilcoxon-signed rank test as shown on the slide is not exactly the same as in the textbook version. Traditionally, the test would sort by differences of values, not by the logarithm of their ratios. In computational mathematical optimization, it's as practice to not use averages, but geometric means. This explains the usage of ratios instead of differences. The Wilcoxon-signed rank test splits the results into two groups depending on whether their ratio is larger or smaller than 1, hence whether the logarithm is positive or negative. It then takes the sums of the rank values of both sets. Loosely speaking, the more different those two sums are, the more likely it is that the one with the larger sum outperforms the one with the smaller sum. Again, a test statistic is computed, for which we know what the distribution would be for random data, and the p-values can be looked up from the statistic. Coming to an end, let's talk about some good practices to follow when conducting computational research. Even if it might be hard to follow all of them, it is worth to strive for as many as possible. A first important point is to choose a suitable test set. One should always check whether there are standard test sets for the particular research field. For example, for experiments with general MIPS, the MIP-lib is the way to go. When studying a particular kind of problems, for example big vehicle routing problems, one should look for a suitable public test set in that field. What did other authors experiment with? Even if their instances are not public, it is worth a try contacting them. Generating test instances on your own should be a last resort. If you come up with your own test instances, and there is something like a standard test set, everyone will challenge you on this. Also, if you write your thesis, it's much more likely that your thesis will have an impact afterwards, if you can show computational results on instances that people know, and for which there is a community interest. Whenever possible, it's advisable to use large test sets, in particular sets that do not only focus on particular cases but are as diverse as possible. Moreover, a test set should ideally contain instances from actual applications, and not only randomly generated ones. The next important thing is to be careful about what to exclude. Often, there are good reasons to exclude certain instances. For example, while developing new techniques that only work on pure binary problems, one would not use the whole MIP-lib for testing, but only the subset of pure binary problems. However, each exclusion should be sufficiently motivated and, moreover, it should be argued why the computational results do not get skewed from it. A similar argument applies when some measures only make sense for all optimal or all timeout instances. Again, it's reasonable to report this only on the respective subset. However, one should always report the number of instances that a particular setting could solve. Care must be taken when splitting test sets. Of course, it is often interesting to split test sets into different categories and find out how things work on easy or hard instances. That's a very natural question to ask. However, a test set should never ever, be split into easy and hard models with respect to only one baseline setting, since this will completely bias the computational experiment. This will have the effect that instances with high performance variability will be sorted by this logic. Instances where the baseline solver was lucky will be considered easy, instances where it was unfortunate will be considered hard. Naturally, an algorithm tested against it will now seemingly show improvements on hard instances. Such a biased selection occurs more often than one would hope for, and has often led to papers being rejected. Not to be misunderstood, splitting a test set in easy and hard instances is perfectly fine, but this should be always done with respect to all the settings being tested. If an instance is easy for all the settings that are being evaluated, then there is no bias induced. The same holds for an instance that is easy for at least one of the settings in comparison. All of them have the same chance of classifying something as easy and hard. One should always report the specification of the machine on which the solver is run, likewise software versions, and working limits that were used. Moreover, when implementing software, it's a great practice to make it publicly available on GitHub, for example, so that other people can redo the experiments, or can conduct experiments with additional components on top, hence continue the proposed research. A researcher should also think about what is a fair comparison. What is the state of the art in the particular field of interest? For example, does the benchmark solver have the same purpose as my newly proposed algorithm? One bad practice is to implement a heuristic and then compare it to an exact solver, concluding that the heuristic, for example, is faster in finding a first feasible solution. In this case, indeed, the comparison should rather be made against other state-of-the-art heuristics, and not against an exact solver. When you develop a method for a specific application, check whether there are other algorithms for this application that you can benchmark against. If it is not public, contact the authors, and yes, in the worst case, re-implement it. To summarize, your question should be, if my algorithm wasn't there, what is the next reasonable thing that people would do to accomplish what I try to do? The answer to this question provides a valid benchmark. A general advice for paper writing is to always clearly state the questions that the paper attempts to answer. In other words, before starting doing computational experiments, one should explain the hypothesis and how it is tested. A completely different topic, which is also important to mention, is that experiments should always be run on idle machines, and not share resources with other programs. In particular, this means that instantiations of the program shouldn't run in parallel to each other, fighting for resources. This can skew the results by up to 50% on an instance-by-instance level. Of course, a researcher should never trust results at a first glance, but investigate outliers, negative and positive ones. A good practice is the use of methods like permutations and statistical tests to double-check the hypothesis. Moreover, it is always preferable to have more than one measure to compare test runs against each other's. Different measures might tell different stories, providing valuable insights on the tested algorithm. Finally, it's also important to report on negative results in papers. If something is tried that didn't work, even without showing a big computational study, it might be useful to report on it. It is, first of all, useful for others, since in this way they can avoid getting into the same pitfalls. Moreover, it proves that the researcher really thought about the problem, tried a lot of alternatives, and had a lot of different ideas. This is a value by itself. There are many journals where computational research can be published. A particularly recommendable one is Mathematical Programming Computation. This journal provides not only a review of the paper, but also a review of the experiments that have been done, including a code review where possible. Moreover, in the journal review at least part of the computational experiments are redone, to check whether the reviewer ends up with the same computational results. This makes MPC results particularly well established. This journal is a really recommended way to get computational studies published.
All right, it's quiz time. First question. Performance variability describes A. Large runtime differences caused by seemingly neutral changes, or B. A method to tell whether a result is significant, or C. A performance measure. Second question. What is not the best practice for computational experiments? A. To use diverse machine setups, or B. To use diverse performance measures, or C. To run on otherwise idle machines. Third question. When comparing runtimes, the significance should be checked by A. A McNamara test, or B. A cyclic shift test, or C. A Wilcoxon-signed rank test. Okay. Short break to think about the answers. And here we go for the solutions. First question. Performance variability describes A. Large runtime differences caused by seemingly neutral changes. B. It is not a good practice to use diverse machine setups for computational experiments. And C. When comparing runtimes, the significance should be checked by a Wilcoxon-signed rank test. So the McNamara test is for categorical data, and the cyclic shift test is a term that I just made up. So, then see you later for my second presentation of today. And until then, bye-bye.